V is a vector space over R or C. An inner product is a function of two variables, takes two vectors, and it spits out a field element. And it satisfies the following properties. For all of u, v, w, and v, and a in the field, it's positive, meaning that the inner product of a vector with itself is non-negative. Now, if I put in two different vectors there, it wouldn't be true anymore. It's definite, meaning that the inner product of a vector with itself is 0 if and only if it was the 0 vector to begin with. It has this additivity property in both the first and the second coordinate. UW plus VW. And two more properties, homogeneity in the first coordinate, meaning that I can pull out a scalar that's multiplying the first vector. And it's conjugate symmetric, meaning that if I flip the order, I have to conjugate. Okay? It's an ordered pair. And this had the consequence that if my scalar multiple was happening in the second factor, in the second part of the second slot of the inner product, pulling it out would result in a complex conjugation. So it's conjugate linear in the second slot. And we went on to use that to define the notion of orthogonality. UV in an inner product space V are orthogonal if UV, the inner product, is equal to 0. Of course, the notion of orthogonality doesn't make sense unless I have an inner product. So only in an inner product space can I talk about that. And from that, we also had a couple of simple results like the Pythagorean theorem, which said that if U and V are orthogonal, vectors in the inner product space V, then the norm of their sum squared is equal to the squared sum of the first one's norm squared plus the second one's norm squared. And that's the usual right triangle situation, but now we've abstracted what we mean by two vectors being perpendicular. So we can talk about right angles in any inner product space. Now, if you think back to when we discussed direct sums and the existence of sort of a complementary subspace. When people see this, there's a common mistake that they make. So let's let V be R2, be the blackboard, and let's pick a vector space U in V. And I'd like to express V as a direct sum of U and some other vector, other subspace W. Now, often as people think about this question, they want to pick this as the subspace W, right? That's kind of the most complementary, but it doesn't matter, right? I could pick any subspace that I like as long as it's not contained in V, and I'll get a direct sum decomposition. That is there will exist a unique u in u and w in w such that v equals u plus w. If I pick this to be w, and I pick a vector here, I just translate this up. So I pick this is my w vector, and this is my u vector. And there's only one such answer. It's a unique answer. I could add them in the other order, of course, but that's still the same answer. Okay. So there's a unique answer, and it doesn't at all depend on this being what we would expect and being perpendicular. So it's kind of an unsatisfying decomposition because it's not canonical. Given u, there's not only one choice of w. There's many different choices of w, even though it feels like it should somehow be distinct. And so orthogonality, if we want to fix that and make this w alone the answer, the way we do that is require that these two subspaces be orthogonal to each other. So the first version of that is to just do that for vectors. And before we talk more about subspaces, so given a vector, now in an inner product space, let u be a vector in v, and v be another vector in v, and let's let v be non-zero. So u is the one we're interested in. So here's u, and v is something else, like that, v. So we'd like to write an orthogonal decomposition of u in terms of v. That is, we'd like it to write it as something in the vector space spanned by v, something in this thing, span of v, plus some other vector, and we'd sure like this other vector to be orthogonal. So that means we want to pick a point in the span of v. We want to pick a multiple of this, pick a good scaling factor for this, such that I land here, and then we need to compute this and show that, in fact, v and, well, in this case, this would be AV, scalar multiple of v, and we want to show that AV inner product with w is 0. That is, that they're orthogonal. And that's sort of a more satisfying decomposition of u into a v part and some complementary part. And it has benefits beyond being satisfying. That is, it's easier to compute things about it, as we'll see. Well, toward such a decomposition, we want u to be equal to AV plus something else. What's something we can add such that we get the right answer? Well, we can add u and then subtract AV. That's tautologically true, but it's also kind of the right picture. I want to say u is equal to AV, and then w is u minus u minus AV. What's left over? This is stuff, so that we want this to be our w. And then v, we want v to be orthogonal to a. We want AV to be orthogonal to w, and that's 0. So we want that to be 0, and that's true if and only if v is orthogonal to w, so long as a is non-negative, or is non-zero. Right? So that means we want 0 to be writable as u minus AV v, the inner product. So when we prove things about inner products, we use their properties to pull things out, break up by linearity. That's exactly what we'll do here. So I want to rewrite this as uv minus a I rearrange these because I want to put the A on this side, so it's a lot easier to keep track of. AVV. Okay. This thing has a name, which is the norm of V. Okay, so all three of these quantities, right, the inner product is a function from V cross V to the field. So that's a field element, that's a field element, and that's a field element. All three of those things are. So I can make whatever manipulations of them I'd like. If our vector V had started out as being 0, unless U was already in the span of V, this project would be hopeless, right? There's no way we could write this decomposition. Since it doesn't, assuming it doesn't start out at 0, we can divide, and we can just set our scaling factor to be UV divided by the norm of V squared. I'm just taking this and solving for A. Okay, this has got to be equal to 0, so add this and divide. So that's the choice we want to make. That's the scaling factor that we have to pick in order to get to a position where the complementary vector will be perpendicular to the space spanned by V. Okay, so our U, our decomposition of U, is it's this quantity, the inner product of U and V, divided by the squared norm of V. You could think about this as being like the amount of U which is in the Vth direction. And of course, that's affected by how big V is to begin with, since it's a scaling factor of V, and that's correcting for that. If V was norm 1, then it would just be that. It's that plus what's left over, which is exactly U minus the same thing. So this is our A, and this is our W, and together this is our orthogonal decomposition. So this is useful for lots of things. The first is to prove a very important and famous inequality that shows up in many different areas of mathematics and also in many areas like statistics and computer science and economics. And this is the Cauchy-Schwarz inequality. So we let V be an inner product space. And let UV be vectors in this space. Then the absolute value of the inner product of UV is less than or equal to norm of U times norm of V. So why do I need to take the absolute value there again? Well, this stuff will always be, norms are always non-negative, but inner products could be anything. Inner products, only if it's VV is guaranteed to be non-negative. Okay, so let's prove that using our orthogonal decomposition of one vector with respect to the other. So take our two vectors. If V is 0, we're done because both sides of this are 0. 0 is orthogonal to everything, and 0 has norm 0. Done. And so assume that V is not 0. Assuming V is not 0, we're going to be able to do this, right? So write the orthogonal decomposition U inner product of uv scaled by the length of v. So the v part plus the w part, where w is just what it was before. W is this guy here, u minus the v part. Okay, so now we have an orthogonal decomposition. We've expressed v in terms of something which is in v and something which is another vector which is orthogonal to that. So we have two orthogonal vectors, and that means that we can use the Pythagorean theorem. That tells me something about u in terms of this decomposition. This is w. It tells me that u, the norm of u squared, is equal to the norm of uv, or the inner product of u and v divided by the norm of v squared times v. The norm squared of that, this was av, the v part of u, plus the norm squared of w. This is just this. And that's possible because we've written this as a sum of two orthogonal vectors. Okay, so if I want to take, so this thing here is just some scalar a. If I want to take the norm of AV, or let's say the norm squared, so it looks exactly the same, the norm of AV squared, that's equal to absolute value norm of V, because this is equal to AV, AV. We pull out the first A without changing it. We pull out the second A and conjugate it, AA bar VV, and that's equal to the square of the modulus of A, VV. Right? That's why that's true. Oops, square there. Okay, so using that fact with A equal to this, the bottom part is already real. The top part, this absolute value, is binding. It could be, I mean, the bottom is already non-negative. This could be real or complex, negative or complex. And so applying this fact, we get that this thing together is equal to absolute value of the inner product of u and v squared divided by the norm of v squared, norm of v squared, plus the norm of w squared. This thing is at least 0, so I can multiply both sides by this. Well, first let's say this is this, since this is at least 0, I can drop it off while saying that this is at least the first part, inner product of u and v squared divided by v squared. Then I take this v and I move it over to the other side. Right? That gives me u squared v squared greater than or equal to uv squared, and then I just take the square root to get the inequality that we wanted to prove. So it really just comes from this notion of orthogonal decomposition and the Pythagorean theorem. So we can recover some other facts from elementary geometry. Geometry in the time of Pythagoras. Not only do we have that theorem about right angles, we also have a general triangle inequality. triangle inequality says that if I have two vectors u and v, in V, which is an inner product space, then the length of u plus v is less than or equal to the length of u plus the length of v. So the picture is here's u, here's v, here's u plus v. Something we expect of any space in which length makes sense. And equality holds, of course, if this is flattened out, right? If u and v are scalar multiples of each other. So it's a proof of the triangle inequality. Well, it seems like a simple thing, but it takes a little bit of work to prove because we're doing this not just for these pictures, but in abstract, right? Just with the structure of an inner product space. So suppose I have my vectors. If you want to prove something in this class about norms or inner products, most of the time it's going to involve taking the norm, the most complex norm expression you see, and expanding it in terms of the inner products and manipulating it with linearity and scalar multiplication, just as we did before. So this is equal to u plus v. U plus v. By linearity, this expands into four terms. u, v. So this is norm of u squared. This is norm of v squared. And then the inside and outside terms, uv, vu. So it's norm of u squared plus norm of v squared plus, you can observe that, well, by conjugate symmetry, I can have this be two uv's at the cost of a conjugation. Okay? So these are two complex numbers. When you think about the complex plane, here's the reals, here's the imaginaries. Let's call this number z. I can think about z as just some vector in the complex plane, something which is real plus something which is imaginary. If I conjugate it, that means I take its imaginary part and I reflect it through this axis, right? I turn plus I something to minus I something. So that's z bar down here. So when I add z and z bar together, the complex parts exactly cancel and the real parts exactly add. So that's equal to u squared plus v squared plus twice the real part of the inner product of u and v. And that's less than u squared plus v squared plus twice the absolute value of the inner product because, well, with equality if it's already real. We're throwing away the complex information, so this will always be bigger. And that is now here's something we can apply. One of the other results we have, we can apply Cauchy-Schwarz to that to get that that's less than or equal to norm of u squared plus norm of v squared plus 2 norm of u norm of v. And that's something nice. I can factor that to just get norm of u plus norm of v squared. And now way back here on the other side, this is what we have on this side. This is what we have on that side. We take the square root. And we get our result. triangle inequality. So you can keep going and recover many of the facts about geometry in R2. One of the other facts you could recover is something called the parallelogram equality, which I'll state but not prove. The pictures, if I have two vectors u and v, this will be v, and this is u. You can add them in two possible ways, well, two possible orders. Of course, when I do that, I get the same answer. So this answer is u plus v. And if instead I subtracted them, I would get this vector, u minus v. And as the picture suggests, these quantities are all related. Well, their lengths are related. U plus v squared, length of u plus v plus the length of u minus v squared is equal to twice u squared, length of u squared plus the norm of v squared. So that proof you can find in the book. I'll omit that one because it's not that enlightening. It's just a calculation very similar to these other calculations. Okay, so now we want to make another definition using the notion of orthogonality. And this is for a list of vectors. So another nice property that a list of vectors could have. A list of vectors, v1, vn, is called orthonormal. Orthogonal, vectors were orthogonal if their inner product was 0. It's orthonormal if their inner products, vi, the inner product of vi and vj, is delta ij. That is, it's 0 if I is not equal to j, and 1 if I equals j. And this happens enough, commonly enough, that this is just a shorthand for that. So in other words, they're pairwise orthogonal. When I is not j, vi, vj inner product is 0. And in the case that they're the same, they're norm 1. The inner product of any vi with itself is 1. Now, one of the challenges in a class like this is always to get you to forget all of the wonderful properties that you learned about vectors that look like this and matrices. Right? And part of why we have to do that is that when you write vectors like that, implicitly, you've chosen a basis, right? And the basis is this basis, 1, 0, 0, 0, 1, 0, 0, 0, 1. That's a basis for, that's what, what's often called the standard basis for R3. And we think about vectors as being linear combinations of these elements, right? So I put an A here, I put a B here, I put a B, C here. It's the same thing. This standard basis is an orthonormal basis, right? Because with the inner product, the dot product, Because if I take any of these two vectors and I dot product them together, I get 0 unless I've chosen the same vector twice. Then I get 1. So that means that this basis, it has lots of nice properties, that it helps you to compute lengths, and it helps you to do all sorts of things. But not every basis for Rn is orthonormal. You can choose lots of other bases, and they have different properties. So one of the things that this is good for is figuring out what it was that was so special about the standard basis that made it so convenient, so that we can extend it to other cases where we don't have a standard basis given to us, or where the choice of orthonormal basis is not obvious in this case. So what are some nice properties of an orthonormal basis or an orthonormal list? I'll give you some examples as well. If E1 up to EM is an orthonormal list, we have the nicest possible description of the norm of a vector expressed as a linear combination of orthonormal bases. So when you've expressed a vector as a linear combination of orthonormal bases like this, you can compute everything you want to know about it, more or less, just from knowing what these are, right? Just from knowing what the coefficients are. So the squared norm is just the sum a1 squared, absolute value of a1 squared, all the way up to the absolute value am squared. That's by the Pythagorean theorem. If you want, reply repeatedly or extended to a multivariate case. Since the norm of any of these individual ai, ei's squared is equal to ai squared, ei squared, and this norm is 1, that's what we had in the Pythagorean theorem, that this was the, and then we have a sum of all of these things, and these vectors are all orthogonal to each other. So whenever we can write V is a sum of ai, ei's, with the ei's orthonormal, then the norm of V is the square root of the sum of the squares. It's also easy to see that an orthonormal list is linearly independent.